So let me wrap up 1 second where we are at right now and what we want to do next, okay? After just showing you some very high-level presentation with some example and to introduce the very idea of supervised learning, what we're doing now, we're giving us a minimum amount of symbols, languages, to give us, the basic ingredients of what we're going to do next, okay? All the course is going to be about algorithm, but this very first class, we actually set up the stage for algorithm by basically saying what is an algorithm and what would be a good algorithm, what would be an optimal algorithm. And to do that, we introduce some theoretical quantities, specifically these guys here, the distribution of the data that we assume to exist but be unknown, or rather known only through IID samples, and the expected risk and the corresponding target function, which are respectively the ideal error over all past and future data, and the best possible solution which an oracle might provide based on all past and future data. The reason why we do this is just because now we can talk about what's optimal, okay, what is an ideal. We would like to get close to that ideal based on our data. It is the part of the theory to tell you once you have an algorithm whether you are indeed close or not to this. But the reason we introduce this is to give you a feeling, hopefully you'll see in a minute, of what could be the good ingredients that allow us to get a good solution. A keyword here is generalization, the idea of being able to go beyond data. And we end up before in these slides where there is a bunch of things. The main thing is we want to try to be as close as possible to the best possible problem, again, the best possible solution, again, ideally. This E here is not the expectation over the data, but is the expectation over all possible past and future data. And here are just two ways to basically say that this is small. Again, we did an expectation because the data set is random. So we need to, in this case, we say that on average, for the average data set, this will be small. And the other thing we need is a couple of ways to say in which sense this is small. One way is asymptotic, meaning as you get more and more data, this will go to 0. It might not go to 0 sometimes if your algorithm is not rich enough, but it might reach a constant, okay, which is the distance to the optimum. The other concept here is more quantitative. It's what I call the sample complexity, and it basically says, suppose that you know something of how fast there's error decrease, then you will be able to tell me how many points I need fixed a precision level for my solution. Okay? This is, again, completely theoretical. It just be a property of my algorithm, and it tells me for which class of problems I can achieve a certain precision. So if you think of designing a learning algorithm, basically two ideas become very clear. The first one is, so Alessandro said you cannot read here. Can you? If I do like this. So here there is the empirical version of the expected risk. It's the average error on the data. Okay? So the basic idea to start the game is often you don't have access to the expected risk because the distribution is fixed but unknown. So what you might try to do is to use the data instead and to try to get the error on the data to be small. So this is what I call fitting the data. One way or another, your only hope is that the data will reflect some properties of the true distribution. And so by making the error on the data small, you'll be able to get some decent solution. Does it make sense? Because you have nothing but the data. So better might be the case that by making the error on the data small, you get something reasonable. The other ingredient is that one should always remember that data are never a full picture. So if you only care about making the error on the data small, you may actually lose capability of predicting new data because you might fall in love with the specificity of the data set you get today without realizing that this is just an incomplete picture of the data you might get tomorrow. Okay, it's just a reflection of the true distribution. And so the other idea which is going to pop out is the idea that the solution is to be stable, meaning that if you change the data and you just a little bit, and you get a completely different solution, this is a bad sign. It might be the sign that in some sense you're just, again, falling in love with the specificity of your data set. These two requirements are clearly in opposition one with the other, because if I create a solution which never changes, for example, I just always say is 1, Okay? This is super stable. No matter what data you give me, I say 1. This is clearly stable, but probably it's going to be horrible in making predictions. On the other hand, if I make something that makes perfect error on my data, it might be the case that I do pretty bad in the future. So this is just one simple example. This is a data set. This will be just a one dimension. This is X, this is Y, this is just a bunch of data. The goal is to produce a fairly good approximation of that solution. This is a very stable solution. I take linear function. You probably go up and a bit down, but not much. And this is actually a solution that does what we call overfitting. It fits perfectly the data. But what might happen is that if I change, say, this point here or this point here, this solution might change completely. Okay? So I'm doing fitting, but that's probably a bad idea. Whereas this one here, this one feels like the one that is capturing the nature of the data. It will make mistakes on the data set, but it probably will be better in the future. How do I choose this one or this one? How do I decide how complex my function should be? Clearly depends on the data. Okay? The more data I have, the more I can believe them. Clearly depends on the problem. The more the problem is simple and regular, the easier it will be to find a good trade-off between fitting and stability. The more the problem looks really like this, the more there is a lot of variability, the more points I will need to resolve this kind of complex behavior. So we will broadly refer to regularization as the idea underlying algorithm that are able to somewhat have some parameter that allows us to go from simple to complex, okay? To somewhat interpolate to a simple solution and a complicated solution. And algorithm will always be made mostly of two steps. One where we have a sequence of possible solutions, and the other one where we actually select one of such solution. The second step we'll call parameter tuning or model selection, okay? And the regularization parameter will be this one parameter. In practice, you might have more than one, that allows to go from this kind of behavior to that kind of behavior, hopefully finding in between something which is good. So let me move on to, no, I have to do this and this. So again, what we have right now is just a terminology that gives us bare minimum amount of symbols and concept to describe the problem, and we introduce somewhat the ideal scenario we would like to solve. Now, in practice, we only have data. So you have to build from data some class of algorithms that is going to be able to perform hopefully as well, and perhaps provably as well, as the target function. What we want to do next is we want to look at the simplest class of algorithm you can think of. It will going to take us very little time to explain the computation in the algorithm. And we will spend a bit more time trying to understand how we can tune the parameters of the algorithm. And we'll see that in this case, we will have to go back and do a little calculation, which is one of the few calculations you'll see in the whole course. And the notion of generalization and the target function and this expected risk are going to pop back in our reasoning. Okay? So the algorithm we want to look at is what we call local methods, okay? Nearest neighbor being the primary example and the primary example we will look at. And the second idea we want to look at is the basic idea of the so-called bias-variance trade-off as one of the guiding principles to do parameter tuning and model selection. And we'll see that somewhat there is a theoretical part of the story and a practical part of the story, but hopefully it will be instructive. So let's look back at the very first example I had, okay? What we need to do now is to predict the price. We already said this, blah, 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 blah. Well, this is actually Sandro's version, so it's now a square meter. And as I said, I don't know if you can see it, but there is a new observation, and the basic idea is let's just look at the house whose size is closest to my house, to the new house, and let's assign to this new house the price of the closest house. Does it make sense? This is what is called the nearest neighbor algorithm. You can replace it, as long as you know how to measure distances between inputs. This can work for any of the examples we saw before. So for the spam, you can take a new text, you go back and the collection of text you already have for which you know whether it's spam or not, you see if there is any text which is close. And then you take the closest and you say, oh, I'm just going to assign the same. I'm going to say if this closest text is spam, I'm going to say that the new text is spam. And otherwise, I'm going to say it's not spam. Or similarly, you can take the case of faces, my face and Carlos' face. Given a new image, you look at the distance between my new image and all the images I have in my data set. I find the closest. If it says me, it's going to say that the new picture contains me. And if it's Carlo, it says it's going to contain Carlo. Okay? As simple as it is, this is the simplest algorithm you can think about. It's only based on the assumption that you're able, which is strong, that you're able to measure distances between inputs. Okay? One text, another text. One image, another image. One house, another house. Again, this is one of the classical cases where writing equation makes it more complicated than thinking what it is in your head. You basically have to order, given a new point, you just measure the distance with all possible other points. And there I just put the Euclidean distance. Okay? I'm assuming these are vectors. And what I do is just compare the first entry to the second entry, the first entry to the first entry, the second entry to the second entry, difference, square, sum, square root. Okay? I don't write it because I'm assuming here that you all know what the Euclidean distance is. Once you find the corresponding index, you go in the data set and you pick the corresponding label, the corresponding output, and you assign this output to the new point x. Does it make sense? Very simple. What is the cost of this? Well, essentially it's the one of computed distance of my new points against everybody else. Okay? And if you do the little computation, if you have two vectors, if D, capital D here is the size of the vector, if you have to measure the distance here, I'm just considering complexity as multiplying two numbers is cost 1. And if I have to compute the distance of two vectors, this basically is equivalent to computing the cost is equivalent to that of computing the inner product of these two vectors. So I have to make product of D numbers, 1 against 1, D times. Okay? And then I have to do this, the new points versus everybody else. So a naive cost would be essentially ND. Okay? It makes sense? It's fairly good. It's fast. And notice here right away that I'm going to do everything here for vectors and Euclidean distance. But as long as you have something where you can define a distance, this works fairly well. Suppose that you have strings. Okay? So 0 binary strings, which are a subset of RD, but a very special one. And suppose that you have some Hamming distance or some other distance that you like among strings. Doesn't matter. Instead of the Euclidean distance here, you just put another distance. And instead of vectors, you just put the Boolean cube, and that's it. And you can think a much more complicated scenario. You think you have each input is a graph. And you have a way to measure distance between graphs. Okay? Then, same. X here is going to be a graph. Xi might be another graph. And then as long as you can compare graphs, you're good to go. So this is general, but you're hiding a lot in what you mean by X and what you mean by the distance. Okay? And the question right away is, how do you choose D? Was that the question? No.
Since the parameters greatly differ in range, shouldn't we apply some sort of normalization?
Yeah. So the question is, if I have my vectors, for example, in the house example, I might have a situation where the parameter might vary a lot in the ranges. Absolutely, yes. So typically, again, I'm hiding everything behind here, okay? If you have, say, images which are pixels, well, maybe that's fine. You can just use that. If you have very heterogeneous measurements, you need to first do a preprocessing, which is not part of our game, where you put all these numbers in the same range so that you can make sense of this distance. Okay? So the fact that I just throw it there, it doesn't mean that it's easy. Okay? In fact, this is the hard part of the problem, which is problem specific. Somebody asked me this during the break. But the point is that this is so problem specific, there are no particular general rules. Yes, you might want to normalize the entries. Yes, you might want to put them zero mean, for example, or things like this. But this is no general rule, okay? The point is that you have, before using this, you have to be sure that you can make sense of a good distance, and then you can start playing. And I'm not giving you indication of how you build the distance. I'm just telling you, once you have the distance, you can play this game. Okay? And this is one of the entry points for prior information. If you have an expert that tells you, oh, look, you should really look at this information and weight them more than this other information, then you should design this part. But this is a design stage of the story, which we won't discuss. Okay? And this will be like a whole week of hacks. So we're not going to discuss that. All right, so as we said before, to do better than this, on one hand, we can complicate the data. But let's just stick to this, because this is not the kind of complication we want to check. One way to make this a bit more complicated is basically, well, but why should I just take the closest house? Maybe that house, the guy that owns it, is crazy and just wants to make 3 million out of a 50 square meter house. Maybe I should be more robust by checking other houses. So instead of just the closest house, you can say, let me also take the second closest, the third closest, the fourth closest, and then I can average the results. Or if I'm in the case of images, I can make them vote. The closest image is Carlo, the second closest is Lorenzo, but the third and the fourth are Carlo. Then I'm going to say that the new picture is Carlo again. So a basic idea is perhaps if I can improve this algorithm, I could, instead of looking at the nearest neighbor, I can look at some neighbors, say the k nearest neighbors. Does it sound like a good idea or a bad idea? And if you know what k nearest neighbor is, don't cheat. Good idea or bad idea?
Well, it depends. It will make all the analysis more complicated, or probably almost a very close result to the easiest way.
So you said email makes the analysis more complicated?
Providing a result that will be very close, probably.
OK, so he's basically saying it's a bad idea, because maybe you're going to make our life harder and probably will not gain much. Who agrees? One that disagrees. Is there anybody disagrees? Is there anyone awake? Well, he says no, so why?
Because you see what's going on around, you know, like you just, with the one neighbor, you just compare, you see just one, you compare your result with just one behavior.
Mm-hmm.
As you get to more neighbor, you have more behavior, so because statistically you have more information, you get more global information.
So he's saying that maybe we're going to make our life harder and get more or less the same result. He's saying, well, maybe not, because by looking at more than one neighbor, we're going to basically get more information. OK?
I mean, you have to try both.
Oh, it's fair. There was no prize or punishment for this question.
That maybe depends on the data, because, for example, if we are distinguishing between positive and negative, and we have a boundary like this, and our new data is near to the boundary line, and from the other side a lot of negative, and from the another side one positive. If I am taking k nearest neighbors, then the voting will be for the negative side, but it should be positive, because it's in the positive side.
Yeah. So it's hard to do the drawing with my hands, but basically what he's saying is it also depends on the problem, right? That's why a lot of people start by saying it depends, because basically you might have a situation where data are very informative, and by taking more than one neighbor, you can blur the situation and confuse, okay? Because one thing that you haven't said, but I think we all agree, is what does it mean, some neighbors? How many? What is some? Is 3 okay? Is 6 okay? Is 10 okay? Is 100 okay? Well, it depends on the problem, right? It might be that one nearest neighbor is fine sometimes, and as he says, we just making our life more complicated. But maybe other situation where what he says, we're basically that by looking at more one neighbor, we get more information. And his exact points to one thing we want to discuss next. So this is the k nearest neighbor, and it's basically just taking, if you want, the average. Okay? Instead of one, again, I show this quickly. I don't want to discuss too much because this is very simple. Instead of just 1 point, you're going to take k points, and if it's a real valued output, you just take the average. Otherwise, basically what you do is that you vote. And if you have 4 points, you take 5, okay? Because otherwise you get a tie.
So it's maybe could be a really good idea if the data is very clustered,
Mm-hmm.
and a bad idea in the case of the data being very, each point being very far from each other.
Mm-hmm. Well, you can think a lot. So what he's saying is that if the data are all clustered together, it might be a good idea to take more k bigger than 1.
I was looking at the previous picture.
I had a picture. Yes. Mm-hmm.
The example, the 300 example,
Yeah.
is in this case is quite a bad idea, because the the data samples are quite far.
Yeah.
Maybe if it was like 100, then there's a big cluster of points,
Mhm.
data points, and so maybe even taking.
Yeah. Let's do the reasoning together. What you're saying is, well, in this case, it seems like a bad idea to average to more than 3, to more than 1, because in some sense this is very close, and now these are far away, and then I'm. But I can also reverse the reasoning and say, look, maybe this is just a mistake. It shouldn't be here, and so if I remove this point, this is going to save me a bit. Okay, if I'm here, I actually don't care too much. I have to take the nearest neighbor, because if I don't take the nearest neighbor, the second nearest neighbor is going to be pretty close. So actually, you can reverse the reasoning and basically say, well, the data are sparse. I might be better off doing some averaging because I make it a little bit more stable. Otherwise, by changing just one point, I can change everything. Whereas if I have a lot of points, maybe I can go for nearest neighbor and just take, 1, because if there's not that one, it's going to be an average. It's going to be more or less like that. But this is what we want to discuss next. So the basic idea, again, here is the algorithm is super simple. It just looks at the distances. It takes the first few points and then either average their output or just make them vote. And so if you're making vote, you want to take something odd so that you can make an actual vote. The cost we already discussed. The fact that you can generalize to any metric we already discussed. Okay. We want to add one more remark. And then we want to move on and think how you use this kind of stuff. And the first remark is basically saying, we kind of already said that you need to choose the distance, okay? Not only that, once you choose the distance, you're basically choosing the way you want to treat the neighbors. And the way we treat the neighbors right now is that we define what's neighbor, and then the neighbor are all the same. They only count with their distance. But one thing you might want to do is basically say, well, let me just say this. Let's just define some other way to measure distances so that in some sense we do a zooming effect, if you want. If things are close, they have to matter a lot. But if things are far away, they should not matter much. So we still keep the distance, but in some sense we take a zooming function on top of it that says when it's small, matters a lot. When it starts to be big, it should decay its importance very quickly. Does it make sense? And then if you look at all these functions, that's kind of what they're doing. One way or another, they're basically zooming in, okay? They're basically just taking an effect that basically says, look, I'm just going to, in some sense, emphasize small distances at the expense of large distances. And so you can generalize these kind of techniques by adding this extra ingredient. And it might come at the price of some extra parameters. So look at, for example, the Gaussians or the Laplacian, but look at the Gaussian, which is the easiest case. What you do here is that by choosing sigma is like the zooming parameter, okay? If sigma is very big, imagine that all things are here, okay? I have one-dimensional input points. Now I have a Gaussian. If I make it very, 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 very large, it's basically as if I didn't put it in, because everything's going to be on the tip of the Gaussian, and it's not going to do anything. It's going to be 1. If I make a very, very small Gaussian, each point is going to see only very few of the others. The distance is actually not going to be 0. But all the other numbers are going to be very, 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 very small, because I just put this bell over each point so that it just sees whatever is very close to it. If you look at the actual number, it will not be 0 because you have tails, but it's basically 0. And now you can play with these extra parameters. You might have, in this case, 2 parameters, the number of neighbors and the size of the bell on top of the parameter. And this technique is what you call parts and windows. For our purposes, you should just know they exist, but we can just move on and ask the other question, which is, how do we use this algorithm? So we're just going to look at the basic nearest neighbor algorithm. And we're exactly going to play the game of changing k and see what happens. So in this case, you have 2 classes, the red one and the black one. So this is x, okay? And just to be clear, where is y? Okay, it's the color. But if you have to draw it, it will be a 3rd dimension, okay? It will be positive here and negative going towards the other direction. And if you look at a function, it would be some kind of function that cuts into the plane. And this area here is the 0 level set. It was the function changes from being positive to being negative. Okay, I'm going to say it again because I remember it always caused me trouble the first time I saw this. This is not f of x, but this is f of x equal 0. F of x is a function which, say, is positive on this side and negative on the other side. Okay, it's a surface in this case. And this is the set of points where it changes from being positive to being negative, and that's what we call the decision surface. Okay, and this, of course, is just a two-dimensional situation. If you go in higher dimension, you cannot draw it anymore, but you have the same K. You have the set of points where the function is 0. Okay, so that's what we're drawing. So this would be a K equal 1. What we're going to do is that I think we're going to keep the training set fixed, and we're going to change K and see what happens. So do you all see the curve? So the curve is pretty jagged. And it even, so when you see stuff like this, if you look in profile, it means that the function, say, is negative. Then it goes up, it becomes positive. So this is like, say, this is a mountain. This here is a valley. And these are two little peaks that goes up and try to. Why does he do that? Well, we don't know. It's basically trying to fit the data well. And it looks like he believes it's a good idea. Probably it's this point here and this point here that creates this wiggle. And the function goes up. OK? If you put k equal 2, it's very similar. If you put k equal 3, you start to see that those spots do disappear. K equal 4 is very similar. K equal 5 is very similar. But you see that it's less and less jagged. It becomes much more regular. And by the time you're 15, this actually becomes fairly regular. And this is kind of what you've been saying in particular, that it depends on the data and depends how the data are distributed. OK? That makes sense? It intuitively makes sense, right? So you can think of a second of these plots, and what you can really think is that basically the stuff that we discussed happens. When you start to look at more neighbors, you're basically saying, well, these guys should really be there. These are really mistakes. And I should actually say that this area is all black. Okay? What you see is that none of these guys matters anymore. And I basically say, oh, these are mistakes, period. Whereas if you take k smaller, you just to basically start to follow those guys one way or another. And you see that for very small k, you actually change where you put the 0, and you change the area that you would call, say, positive or negative. That makes sense? What is the natural question here? How to select k? We allow ourselves an algorithm which, as simple as it is, once you have the distance, seems to be able to go from complex to simple. But how do we decide what's complex and what's simple? It really depends on the data. But it would be nice to know things like, is there an optimal value of k? Does it exist? What does it depend on? If it doesn't exist, maybe we should just not try and just give a couple of trials. I don't know. If it exists, at least we can start think about how we can find it, which is the next question, which is the most important one. If it does exist, what does it depend on, and how do I fix it in practice? So we're first going to answer the first question, and it's going to be a theoretical question. We're going to set up, we're going to go back to our setting and do a couple of calculations, and then we're going to go on and see what you can actually do in practice. Yeah?
I was wondering why in the black region there are those peaks you described earlier for k equal 1 or 2. And I was wondering why those peaks were there in the black area. If the red points are 1.
A 1, what do you mean?
I mean, the binary 1.
So these are, the labels of this would be 1, and it will be -1, and it will be 1. So basically, this should be all negative. So it would be what I call a valley. What happens is that probably, what happens for small k is that basically this function, so imagine that it's like elastic in a way, okay? This is just very rough. But this is basically saying this is positive. This would like to react and to go up and get this. It doesn't manage. It managed to go up only up there. So you should have this peak here, okay? But you don't manage. In some sense, but you should have it. But that's the reason why. If you do it in 1 dimension, so if instead of 2 dimensions, you put 1 dimension, and you put the x's on the line, then you can plot this. So you help me out with this. So if you just take x to be 1 dimensional, f of x will just be a line. And the decision boundary will be just what? one or more points is where I have a line. My function goes from positive to negative, and the very point where this happens is the decision boundary, just as a point. If it happens that it goes up again, it can be more than 1 point, but these are just points. Instead of one-dimensional sets, it's going to be a zero-dimensional set. Same way, if we go in higher dimensions, it will not just be a line, it will be a surface, okay? And in that case, you can go in and draw things and look at them. And you really see, you would see basically that it goes up and down, and you can play a bit and see what happens. Everybody's happy with nearest neighbor. Do you see the algorithm? It's very simple, right? You just compute the distance, and you just average the answer between the first k. And what you're asking now is, how do you choose k? And what the theory and practice tells us about that. We are going to discuss this for nearest neighbors, but this is going to be like a universal argument, okay? You could replace nearest neighbor with pretty much any algorithm you know, where you manage to reduce the problem to 1 or 2 parameters, okay? You basically have the first part of the algorithm taking care of everything but 1 or 2 parameters, and what you're going to do is that you're going to see how you choose those parameters. And again, in the case of nearest neighbor, it's particularly simple, and that's why we chose it. And what we're going to do now is going to first encounter one of the main theoretical ingredients of the whole theory, which is the idea of bias and variance and how we can trade off them. And then see how in practice we can try to go around the limit of the theoretical argument by looking some kind of empirical procedure that is called cross-validation. So, okay, these are the names, but it's very simple. This is just some notation. I have the data. I call it S, nothing new. I put all the points into a matrix. I call it X. Most importantly, this funny K is just is the number of K I use. Say, to make it simple, it's just K from 1 to N, because it doesn't make sense to go after N, okay? And this is my true solution. It depends on the data. I'm not going to put the dependence on K. Okay, so not the true solution. It's the nearest neighbor solution. Given a training set, this is the solution, provide the nearest neighbor. So it's one of those that we've seen a minute ago. Okay? So suppose for a minute that you're playing mathematician and you ask yourself, does an optimal value exist? If it does exist, what should it be? Any guess? What is a good solution?
Probably some value that explains the values of the data. So there are some techniques like the end of methodology and the principal variables which explains the variance of data.
So what he's saying is, perhaps it should be something related to the variance in my data. We didn't even introduce the notion of variance, but it might be this idea that there is some variability in my data, and if I have something that explains so much variability in my data, that's a good idea. Fair enough, but we do give us a language to say what's optimal, right? So what is optimal? What is an optimal solution to the learning problem? Is a solution for which the expected risk is close to that of the target function, okay? So what would be an optimal K in our framework? Well, if I had access to the expected risk, it would something that gives me. Suppose that the game is the following: I give you the data set, and you can compute the solution for many Ks. Then I am the oracle, and you can query me to give you the expected risk of your solution. Okay, it's a kind of an ideal situation. Of course, you don't have an oracle. So again, data set, fix K, get a solution. Then give it to me and says, return the expected risk of this. Same training set, change K, give me the solution, say, return the expected risk of this. If I can choose K that minimizes the expected risk, this will be the optimal thing, because it will be the one that gets me closer to the optimal error. Does it make sense? Can you do it in practice? Yeah, that's why I call it an oracle. Now, when I say test, so sometimes I say test. So here we have to be. So in this game, when we talk about test, it doesn't mean that you have two data sets and you split it in two. You have 50 here and 100 years. It means that you have an oracle, me, I give you 50 points, and I have infinitely many. So you can query me as many times as you want, and you're gonna fit the population, because if you could do it, you would be perfect, okay? So what he's referring to, and you'll see in a minute, is the case where in practice you don't have the oracle, and you can play splitting the data in two. And the problem is that if you see them too many times, bad stuff happens. And for those of you who follow tech news, Baidu knows this very well. But we're going to discuss this in a minute, okay? So right now, the oracle doesn't have access to a finite amount of data, but it actually has access to infinitely many data points. So you don't overfit anything. You just make the solution perfect. The problem is that we don't have oracles, okay? So what we're going to do is, first, we're going to assume that the oracle exists and just see how the optimal choice given by the oracle for the regression parameter would look like. What does it depend on, okay? And we're going to try, you will see that basically this idea of overfitting and stability that I throw at you when you accepted them actually comes out of a theoretical argument. And then we're going to see how we can do in practice once we don't have access to the oracle, okay? Is the plan clear? So this part is a bit more mathy, and there are just 2 points where you should do a calculation, and I'm going to skip them, okay? I just want to show you the result. But we can discuss it later, or we can do it as an exercise. So here's what I do. If you remember, the expected risk is just this quantity average over all possible x and y. This is optimal, okay? And then I still have the dependence on the training set, and that's why I take this other expectation. If you now look at this for any fixed training set, this whole thing is just a function of k. That's the only three thing, right? And so this is what you can query the oracle for. You fix k, produce fs of k, and tell me, give me this number. Now the question is, this is just a real valued function, okay? Just I give you k, you give me a number. And you can ask questions like, does a minimum exist? How does this function look like? Is it like this, or it is like this? Makes sense, right? Because if it was like this, I would say, oh, a nice minimum exists. That's a k I would like to. How do I get it? But if it's like this, well, we know that the problem might be very hard, even if I had an oracle. Okay, let alone the fact that I don't have it. But even if I had an oracle, if the function looks like this, finding the minimum of this function is very complicated, right? So what we want to do next is, again, we're going to be theoretical for a little bit, and we just try to understand if we can understand a bit the properties of the minimization of that function with respect to k. And it's not very easy, because when you want to study a minimum, what do you do, usually? You take the derivative, you set it equal to 0, convexity, blah, 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 blah. But the dependence of this function over k is not simple, right? It's complicated. It's the function which is the sum over a bunch of things, and it depends on all this stuff. It's not really clear how you can derive with respect to k. So we're going to do another route. In some sense, we're going to find a technique to study the minimum of this function and get an idea how it looks like with respect to k, and hopefully we will learn something along the way. When we'll be done with that, we're going to try to see how we can work in practice. Is the plan clear? This is going to be the most painful part of this whole course, so you better be alive now. I already said everything. OK, so to make our life a little bit less miserable, I'm going to just take a special case, OK? Instead of working in full generality for any distribution, we're going to be theoretical, but we're going to assume that the distribution is just this. Okay? So I'm assuming that my distribution, it comes from a regression model, just because it makes my life a bit easier. So instead of any possible distribution over x and y, I'm just going to consider this one here. Well, actually, to make your life easier when you do the calculation. And I'm assuming the noise to be 0 mean and with some variance sigma square. Again, this means that if I have the perfect function, it still will do a mistake. You cannot go beyond sigma square. That's the minimum amount of error you have to allow yourself in this game. OK? OK? So I take this special case. Also, this is what I'm going to do. Ignore this line first. So what I do is that I fix x. You see, in this definition here, I first take expectation with respect to x and y, and then with respect to the training set. But if you remember, this one here, I can split in x and y given x. Okay? And to make my life easier, I want to fix x. And to minimize this for every fixed x. The reason why I do this is because this becomes a number if I fix x. So I can literally just work with real valued functions. Okay? So this makes my life a bit easier. It's not substantial, but I can do it. So what you do is that you split this expectation over x and y given x, and then you fix x once and for all. And you just work with this for fixed x. Okay? If you don't appreciate the difference between the two, just stare at this for a second, and this is what we want to study. I can convince you that this is pretty much equivalent to what we were doing before. So what we want to do, instead of studying this for any possible x, we fix x, and we ask what is the optimal k for that fixed x. And we'll see that the answer doesn't depend on the specific x. Okay? These silences, you have no idea how horrible they are. But the question, so it is clear what I want to do next. What I want to do next is look at this quantity, which is the expected risk of my solution, the one I can query the oracle for. I fix x, and then I want to understand the behavior of that function as a function of k. Okay? That's what I want to do next. So what we're going to do is that we're going to start massage this until we get a better feeling of how it looks like as a function of k. And we'll see that we can get up to a point. Okay? So first what you do, the first massage is that you take y, but we assume that y looks like this. So we can replace y with this here. Make sense? I just take y and replace it. But then what you can do is the following. Basically, I want to treat this as one term, and this is another term. So I want to treat it as a plus b squared. Okay? And we'll consider these two to be a, and this one to be b. And I want to take the square. That is going to give me a squared plus b squared minus 2, well, plus 2ac. Okay? Hopefully nobody's going to enter in this moment in the class. And what I claim, so, is that basically you get a squared, b squared, but the two ab terms disappears. Okay? Again, I want to look at these as the terms a, and these as the term b. So if you see, you get a squared. I claim that this one here is b squared. Why? Well, it's written here. Because e delta square is just sigma square, and that's what's written here. And what's missing is the product of this term and delta. Correct? I should have this extra term. But it's 0. Why is it 0? What? Say it again.
The noise is centered.
The noise is centered. Yes, exactly. So what happens is basically that you have to do, imagine that here you have to do the product of this guy and this guy times this. Okay? But the only things that depends on y given x, if you want, which is, in this case, depends on delta, is this term here. So when you let the expectation go and hit this, you have 2a times b. But when you put the expectation in front of b, which is this guy, it's 0. And so that terms disappear. Okay? So if you follow what I just said in words, good. If you don't, try to do it on paper. But believe me otherwise that this is what you get. And you just basically use the linearity of the inner product and the fact that the random variable is 0 mean, or centered, as he said. OK, fair enough. So we see, now look at this result. OK, and just check what it means. It basically means when I look at the expected risk, what I really should do is, what I'm actually effectively doing is checking whether my function is close to the best function plus something, which is basically the error of the best. And this is something I just cannot below. Okay? This is the price I pay for this no matter what. Does it make sense? So even after the calculation, we start to see something that we kind of expected, but here we see an equation that proves it. The distance between my function and the best plus essentially the error of the best. All right, so now we replaced the study of this with the study of this. what we want to do next is, we don't really know, again, how to differentiate with respect to k. What we want to do is to introduce some intermediate object, which is going to be a theoretical object, which is not this and is not this, but is something in between. And then we're going to split these in two terms and check how these terms look like. To do this, the intermediate object we want to check is kind of an idealized version of the algorithm. It's idealized in the sense that the real algorithm doesn't look like this. How does it look like? It does take the nearest neighbors, but then it averages what? Y. Instead, this guy, again, it's an oracle kind of guy, because he knows the actual value of the true function at those points is limited in that he doesn't see the whole data sets, but it's ideal in that he doesn't see the noise, essentially. Okay? This is in between the perfect function, which would be the one that produced just f star x, and the practical function, which is the one that produced the average of the y's. So this is one introduced as an intermediate step. If you think about it just 1 second, it's easy to see that this is exactly the expectation of the practical guy. Because again, if you take the expectation of the y, you're going to get you take the expectation of this for fixed x, you get f star x, and then you take the expectation of this, which is 0. So if you take the practical algorithm, the one with y, and now you take expectation, you get f star x, and then the delta goes away. So if you want, this is the expected version of your algorithm. Is the mean of your algorithm with respect to all possible noise levels. If you go on and now add and subtract this one function in the expression I showed you before, this is what you get. You still get this sigma square, forget it. And then you get the difference between this guy, which is this, and the guy you get in practice. So is something minus its expectation square. That's what you call a variance. Okay? Notice that it doesn't depend on, it depends on f star through this guy. And then you have this. The nature of this is funny. Okay? It's basically saying that it's a price you pay, but instead of using f star x, by doing the average of this f star xl. And that's what you call a bias. What we want to do next is understand the nature of this term and the nature of this term with respect to k. And what you will see is that it's fairly easy to understand the behavior of this. This will be more like a reasoning than just an equation. Okay? Here, what I'm doing is just these two guys, they do have an explicit expression, and these are sum over k over the same set. This one is going to be yl, and this is going to be f star x. Okay? But if you think about it, then it means that you have y, its expectation, sum k times. But these are independent random variable, so the variance of the sum is given by the sum of the variances. Okay? And again, if you know what I'm talking about, good. Otherwise, go check your probability 0. And so what you can check is that by using this fact, it's just an equality. Basically, what I'm doing is I'm taking this summation, which is inside. I take it outside, and I still have this square. So what I need is this 1 over k square. Okay? This calculation here is, again, just the fact that you have sum of the variance of a sum of independent random variable, which is equal to the sum of the variances. Okay? This is one step away. But then once you have this, this is just the usual noise. Okay? Sum k times. So this is just what? Is yl minus its mean square, but that's just the noise, right? Y minus f star is just delta, because y is f star plus delta. So this is just delta square. But how much is delta square? Sigma square, right? It means that I have sigma square, sum k times, so I get k sigma square, divided by k square. So putting all things together, you basically have that the variance term is going to be sigma squared divided by k plus sigma squared, which was already there before. So this is basically saying, look, when you look at the true algorithm and how this deviates from the ideal algorithm, if you take a big k, they're going to behave similarly, which makes sense with our picture, right? It was much more stable. For big k, the trend was that my function was not changing much. It depends less on the data if you want. Whereas if you put small k, it depends a lot on the data, and so it might change quite a bit once I change my data. And this tells you exactly how it behaves. It behaves inverse proportionally. And of course, this also depends on the problem, as somebody says. And in fact, sigma appears there. Big or small k depends on how big or small is the noise. OK? But just on the noise. F star, in some sense, disappeared. Only the noise enters the picture. But this kind of is reassuring. It's a first bit of the explanation of how changing k would affect my solution. If you were to ignore the presence of this, what would be the best possible value of k? The maximum, right? Why? Because I'm not asking to be close to the ideal. I'm just asking to be close to something very stable. I'm ignoring the fitting part. I'm just saying, give me something stable. And it says, oh, take everything, just average everybody. This is as stable as it gets. This is what you should do. But then I have to check what this is doing. And again, this one getting an analytical expression, it's a bit harder. But basically what this is doing is basically saying, look, if you, and this is a bit more hand-wavy, if you take k small, and if 2 points are close enough, then my f star xl is going to be pretty close to f star x. If I start to increase k, I'm going to let a lot of other points, x1, xl, blur my prediction of f star x. So intuitively, what happens is that for small k, I get a better prediction of f star x. Again, because this guy doesn't have the noise inside, right? He knows f star. But if you augment k, then you're going to blur, and eventually you're going to take very far away point to predict this one guy here through the correct function. So you're going to let very far away values of your function affect the way you predict the point here, the function here. So roughly speaking, you can imagine this as an opposite dependence on k. If k is small, this will be small. And if k is big, this becomes big, because I'm blurring my prediction. That make sense? More or less? All lost? So again, for small k, I can assume that if my points are sufficiently, say, dense, that this is a good proxy of my true function f star. Whereas for sure, if I start to go far away, I'm going to blur and spoil my solution. If you now put these two together, in some sense, up to this approximation that we didn't do of the bias term, you see that basically you have, if you believe this last argument, you have that this guy is equal to the sum of two terms. One is decreasing in k, and one is increasing in k, which basically means that my function is the sum of two functions, OK? And so now I didn't draw it, but you can now draw the function, which is the sum. And you would basically have that around here, which should be more or less around the optimum, the minimum, so more or less around the crossing points, you have the minimum of the sum. Again, the variance, what it does is that it decreases if you increase k, because you're becoming very stable. So the variance doesn't change much. Whereas the bias gets spoiled with increasing k. This one here essentially depends only on the noise. This one here actually depends on the function. Because clearly, if my function is very regular, it might be a better idea to start to even average a bit around the points. If my function is very complicated, the very moment I put k slightly bigger than 1, I immediately start to spoil everything, because I start to get points which are in some sense very different, where my function is very different. Okay? So it depends on sigma, and this depends on f star. So this is what I promised you to be the first part of my story. Okay? By looking at the theoretical property of the expected risk as a function of k, you basically understand that this object is essentially made of two components. What I might call a variance. that basically capture the idea of stability of my estimator, and the idea of the bias that capture the idea of how much you are sacrificing to get stable behavior. The variance term that does depend on the noise, and the bias term that does depend on the target function. And in some sense, to me, this is instructive. It tells me a bit what are some, well, it gives me somewhat a formalization of an intuition that we said all along, which is that learning, optimal learning, is a trade-off between stability and fitting. And so here is one way to see it, okay? And you also see, to some extent, why it can be useful to check the expected risk, to introduce the whole framework that tells me that there is an underlying model so that I can talk about optimality. Because otherwise, this would just be left to a heuristic, and I say, oh, I do this, and you do that. Well, let's see what happens. So at least now, at least here, theoretically, it says that this procedure is optimal in a precise sense. Okay? So in practice, if you want to turn this into an algorithm, you need to have, so this one is fine, essentially. Okay? This is up to the fact that you might need to know sigma square. You can compute that quantity. The problem is that you need a sharp estimate of this quantity. And the problem is that this quantity depends on a star, so it's hard to get a sharp estimate. In practice, there are a bunch of ways of trying to go around this problem. One way is essentially to replace this with an empirical quantity, something like an empirical risk. And what you end up doing is optimizing, instead of this, an empirical version of this. Would replace this with a data-driven quantity. And this goes in the direction of methods so-called like complexity regularization, structural risk minimization, ICAIC or BIC criterion. There's a whole bunch of techniques that are based on the idea of finding a good proxy of this functional by replacing this with something you can compute in practice. The other idea is the one I'm going to talk about, is the one that basically says, look, what I'm going to do is that I'm going to split the data so that I use some part of the data to compute f hat s, and then some other part of the data to compute this expectation here. So if you want to have a training and a validation set. So this is going to become S, and this is going to become S prime, two separate ones. And the idea is that by using this second part of the data, I can get a good proxy of this term. Again, you can view this as another way to study the minimum of that problem. And this actually is something you can compute in practice. So this is the basic and most simple way to do cross-validation. It's called holdout cross-validation. What you do is that you take the data, you split in one set, and then a second set. You call the first one training, and the second one, I like to call it validation rather than test. The test is that one thing that you never should look at, okay? How do you split them in two? For the time being, let's just say 50-50 or 70-30, perhaps better. 70% for training, 30% for test. Why? Because you can show that any proportional way of doing it in theory works the same, and this seems like a reasonable one. Then what do you do? Well, nothing. The obvious thing. You train for different k on the first set, the training set, and then you check the error you make on the part of the data you left out. Okay? So this one here just depends on the size of the validation set. Okay? And the important thing is that the set where you compute the solution and the set you use to test its properties are independent to each other, statistically independent. And so this is what allows you to prove that, in fact, this is a good idea. So the basic idea again, and then at that point, you just minimize over k. Once you have this quantity, you minimize over k, and you pick that k. So one way to justify this procedure, coming from the theoretical argument we just discussed, is basically just saying, look, what I'm going to do is just, I know that I should minimize the expected risk. I cannot. So what I'm going to do is that I'm going to split my data in two, and then I'm going to use half of it to do a good proxy of the expected risk. OK, that's an argument. If you want another more heuristic argument, is the one that basically says, look, if I look at the training set, I might just fall in love with the training set itself. If I just try to minimize the error in the training set, I just get specialized to this set. So what I'm going to do is that I'm going to take another set, and use it as a test bed to try to see what is common between these two sets. And that's what I should keep. Okay? If I see that by changing k, I minimize the error on this, it means that in some sense I'm good not only on the training set, but also on future data. And by doing this, I'm trying to check, in some sense intuitively, try to understand what's common among these two data sets. Okay? This is just a hand-wavy explanation. The one I showed before is a bit more formal and can be proved, in fact. Yeah?
Shouldn't I also investigate the learning rate?
What do you mean?
That's the okay. I was thinking about this. Let's say that we use 70% to train my model.
Yes.
Actually, we say that more data you give the model, the more the model will be precise and sharp.
Mm-hmm.
So I'm actually sacrificing a percentage of my sharpness in order to understand which is the best model. So I suppose that once I would identify which is the best K with the 70% of the training set, I will then provide it 100% for the training. So
Mm-hmm.
let's say it's 2, then I will add a 30% that I used to check, and so I will have 100%. But what if the learning rate of 3 is faster than 2, and I have a tipping point at 8%?
I lost you the last part where I have 3 and 2 and the
Okay,
tip.
learning rate is, if I give you 10% more of data, the sharpness of
Yeah.
the model will increase of 8%.
Yeah. Yeah.
Now what if, let's say I find that 70% is 2.
No, yeah, okay, but you don't have that. So, okay, so the question is a bit complicated, so I try to split it in two parts, okay? So the first part of what he's saying is, what you do in this kind of case is that you basically split the data in two, 70 and 30. Then you pick the K that is based on this 30 while you train everything on 70 a few times. Then typically what you do is that you know that the more data, the better. So what you do is that you put them back together and you train on 100 points, okay, or 100% of data. So what you see, and what you need to know is, okay, but the K I chose was the one that was good for 70%. Is the one I should use on 100 is the same? Okay, that's a very good and practical question. So the short answer is, I think most people actually don't care in practice, because oftentimes between 70 and 100, it doesn't change that much. What you should really do is that you should know what, okay, this is the first, this was the question, okay, and this is the sloppy answer. The slightly less sloppy answer, what he was saying was, maybe I should know something about the learning rate, which is something that tells me, in some sense, how error scales with K and N and everything else. Because if I knew it, I could update my choice and say, look, if I have 70, this is the best choice. If you have 100, you should use this other choice, which is the scale version of the optimal parameter. Say, for example, something like, for 70%, the optimal K is this K hat. But if you get 100%, you do some kind of rescaling, for example. And in fact, that's what you should do. And basically what you should do, you can prove theoretically what you should do is in some sense a proportion. Basically, you say this one is the best for 70, what should be the best for 100? And you just do a proportion, so you do K hat divided by 100 divided by 70. And this should be the one, update one. Okay, and this does come from a learning rate argument.
So if it's 3 for 70, I should set 4 for 100.
Yeah.
Okay.
Yes.
Or almost 4.
Something like that. It goes in that direction. Mm-hmm. Okay.
Does that apply for all parameters that you might learn?
Say it again?
Does that apply for all parameters that you might learn, different kinds of learning?
Yeah. So
even though you've learned using cross-validation, then you still must update it given the amount of training and training validation.
yeah. So because I mean, again, the question. So what you asked me is, if you have other parameters, okay, and you're using this kind of cross-validation techniques, I think the question is, should you still do this adjustment in the parameter once you, instead of using adjusted percentage, you retrain on everything? Is that your question? Yeah, the answer is yes. So but let me say, use this as an excuse to make one comment. So one comment is, in practice, you might have other algorithm with other parameters, or maybe this algorithm with extra parameters. For example, you can use this zooming function or this kernel function, okay? In that case, you will have that this function is a function of more than one parameter. This calculation won't hold anymore. You will have to redo it in order to justify this bias-variance trade-off. But essentially, you can do it in many, many, many cases. I should also say that whatever you will see in this course follows kind of a non-parametric and somewhat frequentist, I guess, approach, meaning that we're not going to start with probabilities and try to estimate probabilities. What we're going to do is to state problems and try to solve exactly the problem we're looking for. Exactly find a solution of the question we're stated. For example, I have a classification problem. I just want to predict 1 or minus 1. I'm not going to give you the probability of 1 and minus 1. I'm just going to give you a rule that says 1 or minus 1. You want to predict the houses, prices. I'm just going to give you the price of the new house. And this is in contrast with the broader class of techniques that somewhat always put probability in the center and always try to estimate probabilities. Why is this? Is this because estimating probability is in principle a bad idea? Absolutely not. That's a fantastic idea. It's the holy grail. If you can always estimate probability, that's fantastic. To some extent, one price you pay sometimes is that you have some general principles, and then the way I see it is that sometimes by shooting for a more ambitious objective, sometimes you end up in computation with our nastier. So what we're going to do is oftentimes shoot for something less and try to keep the computation as controlled as possible. So we're always going to try to, as I'm doing here, try to get problems which are either super simple or convex so that they can be solved with techniques that do come with guarantees, and then just leave 1, 2, 3 parameters to this kind of cross-validation criterion, but not more. Because again, this kind of cross-validation argument doesn't come with particular guarantees in terms of how long it's going to take, okay? And this is somewhat in contrast with the other criterion where what you do is basically saying, I'm just going to take a bunch of parameters and I'm just going to, say, optimize 5,000 parameters through cross-validation. So in our game, in some sense, we try to keep all the parameters in the optimization in the first part, and then 1 or 2 to just control this complexity, okay? And this is kind of the approach we take. And so in some sense, you will see tomorrow that this will lead us to either essentially to convex optimization problem, or more generally constrained optimization problem, where in some sense the fitting part comes as an optimization objective, and the stability requirement comes in as some kind of penalty or constrained objective. Okay? Other comments or questions? So again, in practice, when you do this procedure where you split the data in two, you still have choices to make, right? We already discussed the percentage of points you want to use for training and test, but also which set of points you use for training and which set of points you use for validation. Do you think that matters? And let's skip the part where you say it depends, and let's just go to the one after. Yes, it depends. On what? Is the question clear?
If the training and the validation set are equally distributed among all the possible values, maybe they work well. If they are really focalized on a class or a certain value, you learn something wrong.
So what he's saying is, if the training and the validation somewhat are really similar, can I say it like that, then well, it doesn't matter that much. True. When do you think that happens?
So all the data set is equally distributed.
But the whole data set is equal. It depends a bit what you mean. The whole data set comes from the same distribution. Okay? So I think the intuition is when the data set is fairly similar, all the things are very similar to each other. But when does that happen?
I should randomize the 30%.
But that's already solving the question. But what I want to know is, let's follow that reasoning just 1 second, okay? He's basically saying, if my data are fairly uniform and nice and very similar to each other, then probably I can just split in some way. And he's already saying, well, you should randomize. Okay, but let's wait 1 second until we convince ourselves that we have to randomize, which is definitely something you want to do. So the point I want to make is just, when is that this kind of similarity among all my data set points is going to happen? Well, probably when I have a huge data set, okay? What does it mean huge? I don't know. But if it's big, right? So if I have, say, in the one-dimensional problem, I have 2 million points, they're probably big. And probably if I also have images, if I have 1 billion images, it's good, okay? These days we have data sets where we have, say, 1 million images, okay, or 10 million images. You start to be in the direction where maybe the splitting, you can just one. Sometimes it's even just a computational reason because you just don't have the time to do more than once. But other times it's because the data is big enough that you can hope for that one split is going to be enough. Certainly, splitting more than once is not going to hurt. Okay, it's going to make your life miserable computationally, but you can afford it. That's probably it's a good idea. Why? Because by splitting more than once, you, in some sense, go away from bad luck. The bad luck of having split in exactly the one part where this 30% is absolutely not similar to the 70% or the other way around. So the simplest thing you can do, and I think that's what's implemented in the lab, and that's why it's mentioned here, is that you just randomize and you do kind of an exhaustive holdout search where you split 70-30 and then again by changing the way you split, and then again, and then again. Then you compute the average error, you minimize that, okay? In practice, rather than doing this splitting, where the bad thing that might happen is that in two subsequent split, say training, validation, if you just do split them at random, it might be that there is a big overlap between this training set and this training set, okay? So what people end up doing oftentimes is what is called k-fold cross-validation. What you do is basically you take a data set and you split, say, in 5 sets. Then you take out the last part and use 4 for training, and then you test on the 5th. And then you repeat by putting this back in and taking away the 4th part, okay? And then you keep on going. So again, you divide in 5, you take away 1 bit, training on the rest, put it back in, take away the next one over. And the reason why you do this is because you minimize the amount of overlap between the test in one step and the test in the other step. In fact, they're completely independent. And in fact, this is, if you want, is the cross-validation is really the one I show you. Holdout cross-validation is the very basic example of cross-validation techniques. And you can do this kind of exhaustive holdout, or you can do k-fold. The extreme case of k-fold cross-validation is what? Leave one out, where basically what you do is that you take as many points, as many groups as the number of points, take 1 point out, and so on and so forth, okay? Now, until a while ago, I think there were essentially no results on k-fold cross-validation and stuff like that. Now there are a bunch of results that basically shows that all these methods are actually optimal. What does it mean? You can prove that they work as well as if you had an oracle who you can query the exact solution. Okay? Does it mean that these are perfect in practice? No, because, for example, we are not looking at the variance of this kind of stuff. And in this kind of theoretical argument, there are constants all over the place that might actually play a big role in practice. But it does give you an idea that cross-validation is not just a hack, but it's something where you can prove guarantees, which oftentimes is a good thing in life, so that it guides you toward things that you can prove other things, and so on and so forth. Notice that for cross-validation, there is an inherent computational statistical trade-off inside, as we said, because again, of course you would like to use as many splits as possible, but this comes to a cost, okay? And so it's an open question and there are not very good solutions. The one of basically being able to compute the solution corresponding to different splits without recomputing everything all the time, okay? You could assume that the different splits are similar between each other, so you might reuse the computation you've done for one case to compute the other case, but this is not really clear how to do it in the best possible way. Notice also that when you talk about the computational complexity of an algorithm, for example, we checked the one on nearest neighbor, I show you how complex it is, and tomorrow you'll see others. I think it's very good and refreshing and important to always realize that an algorithm is never the one where you fix the complexity parameter, say k, or some other parameter that you know, and compute things. Because you always have to compute the solution corresponding to different parameters, okay? For k nearest neighbor, it doesn't really matter, because the main computation that you do is basically computing distances, and once you've done that, you're done. You just have to, change the windows of k of neighbors you want to look at. So it doesn't really matter. But you'll see tomorrow there are many, many other algorithms where once you fix the equivalent of k, you have a computation. But then for another k, you have to do as many computation. Okay? And that's what people sometimes call a regularization path, which is not one solution, but a set of solutions corresponding to different complexity in a very loose sense, or complication of your potential solution. Okay? And this is just, I guess, just to give you a feeling of how these things would look like. If you put here, K, and you put the training set and the validation error, what you're going to see is that the training set is going to get better for small k, period. Okay, you just fit. But this guy, what he does is that he goes down a bit, and then he goes up. For small k, you start to hit overfitting. Okay, and if you want, this is the picture of regularization. This is what sometimes is called a learning curve. And what you see is it is not as nice as you would like it to be because there are random effects. And that's why you would like to do it perhaps in practice you want to do this many times because then you can try to average out this curve a little bit, okay? And you see that this problem you see why we try to keep this problem simple using just 1 or 2 regularization parameter because that curve is not very nice. Until you take 1 or 2 parameters, you can you hack your way around finding this minimum. But if it starts to be, say, 5, 6, 10, 100 parameters, then God knows where you're hitting the minimum and where you just get stuck in a point like this. Okay? So then this is, in some sense, is one reason behind the philosophy. You're just looking at few regularization parameters. Okay, so this kind of wrap up what I wanted to say this morning. Again, so let me just try to take a step back and try to list what we've seen so far. So again, the first part basically was what we're talking about when we're talking about machine learning. These are some examples. And when I say machine learning, I should really say supervised learning, which is perhaps the subset of the field which is more mature, both from a practical and a theoretical point of view. And that's why we focused for a couple of days on it. And the whole game was basically introduced this idea of input and output, what sometimes people call learning from example paradigm. The pairs, X and Y, are examples, and we want to learn from example of potential answers to the problem. I give you X, and the answer is Y. Give me a new X. What is the answer for this? Okay. Then we introduced the basic concepts of statistical learning theory, the training set from a probability distribution that encompass all the source of uncertainty in the problem, loss function to measure errors for deterministic rule in an uncertain environment, and then expected risk and target function, if you want consistency and generalization, to set the stage of what does it mean to have a good algorithm or even an optimal algorithm. In the second part of the morning, what we introduced is arguably the simplest type of algorithm you can think of. Sometimes so local methods, because they basically just look at distance. They don't make an overall model. They only do implicit an overall model of your data. They only look at a local neighbor to make decisions. And we use this as an excuse to think about parameter tuning and model selection, introducing this basic idea of regularization as a trade-off between stability and fitting, and bias variance as the guiding principle that tells us what does it mean to have fitting and stability, and showing that it does indeed exist an optimal solution to the problem. And then finally, in practice, introduce cross-validation as a way to pursue these kind of questions in a practical, data-driven way. One question is, what's next? Okay, what's left? Because we do have an algorithm. We do have a way to tune it. I already admitted that I'm going to tell you nothing for the rest of the week in the way you choose the similarity or distance function. So what's left to be said? This beautiful picture, which I think Alessandro stole somewhere because I would never have done this, for example. It's kind of one reason to be here tomorrow too, and without go to the beach, I hope. The idea is basically the following. The very notion of being close, it's messed up as soon as you go in high dimension. And high dimension is 5, okay? And here is just a picture to see it. Our intuition of what it means to be close is that it's very naive and it's based on 1, 2, 3-dimensional world. But what you already see is that to some extent, this picture here shows you that, what does it mean to be close in 1 dimension? What does it mean to be close in many dimensions? And what you see is that, in some sense, the space is much bigger, okay? And as soon as you go to higher dimension, it gets even bigger and bigger. What they usually do is this little calculation that I invite you to do over lunch just to have some fun. Take a unit cube, okay? And ask yourself, how big is the cube that contains 1% of the volume of the total cube? Okay? So again, take a unit cube, and then ask yourself how big is the little cube inside of the big cube that contains 1% of the volume. Do this calculation for dimension 2, 3, 4, 5, 6, 7. Okay? What you will see is basically that even at dimension relatively small, say 10, the small cube is essentially as big as the whole cube. What this shows is that, and it's just one possible way, there are many, many other ways of seeing this, is that distances in high dimension are kind of screwed up, and we don't have a very good way to understand what does it mean to be local. So what we're going to try to do next is, instead of looking at local methods, we're going to try to look at global methods. What these methods do is basically take advantage of the fact that if you have a function which is regular, say, I don't know, is smooth, or the simplest case is a line, by learning the values of function here, if you can use also points that are far away, okay? And you can use these to leverage the information of points far away in the space. The idea here is that a function might change. You might have very few points in a region of the space, but you might have points in other region of the space that helps you making this prediction. A line is the typical case, right? Because a line is just one parameter. If you learn it here, or here, or here, it's all the same. If you use the model, you get a much better prediction. Go in high dimension. It's not one parameter, it's many. But it's still true that you have a bunch of points. You get much better than if you just look locally. And of course, instead of a line, I can take a function and move, that varies smoothly. If the function is crazy, then looking at points which are far away, working globally or working locally, it's not going to give you much. But if the function does have some regularity properties, so you might be better off trying to working globally instead of locally. So what we're going to do tomorrow, we are basically going to start by making assumption about the form of the solution. Okay? So here, if you think about it, we didn't make any assumption. We got these crazy curves, okay, that came out just by changing k. But if you ask me, what kind of curve is that? Is that a polynomial, or is it piecewise, or how many pieces? But it's hard to say. It's actually, you can check this. It's essentially a piecewise constant function, or piecewise linear. It depends how you set it up. I guess piecewise constant is what it is. But we didn't start by making a model of the function we're looking for. This is what one would call a non-parametric model. So what you're going to see tomorrow is that you're going to start by making assumption of the model, working parametrically, and then introduce the notion of kernel as a way to still to work globally, but with non-parametric model. Okay? So kernels are perhaps the simplest way and the most, let's say, rigorous way to work with global non-parametric models of learning. Also, that's where we're going to be here tomorrow. All right, so I guess I'm done.